context. So kindly wait for day 2 and second session today, and even we are having 2 sessions tomorrow, then 2 sessions day after tomorrow. So most of the questions which have been posted will be taken up in the sequence by Akash sir during the demonstrations. Then you on the maybe end of the second day, if your topic related to the question has been covered, your query has been not answered, then you can post the question. So otherwise, it will be a very large number of questions, so we'll not be able to take up the related questions also. That is my humble request to all the participants that kindly post questions related to the topic of the session, please. So with this request, now I hand over the session to Raj sir for further processing.
Thank you, sir. So in the previous case, we saw that we had started a parametric simulation of patch antenna. So now we are going to see the result and see, first of all, make a parametric optimization of those things, and then view the different feeding techniques which are utilized other than the inset feed. So I'll share the screen now. So the screen is shared. The simulation is complete now. So we will check one by one what are the results that have been obtained. I'll check it now. We go to results. First of all, click on solution data. So the result will go to convergence tab, and here check. So the maximum number of passes is 15 out here. Maximum number of passes is 15 out here. What has happened is first time 1177 elements had been created. The next step, it has been increased by 30% to 1532. And the residual delta S, which is the difference between the previous and the new S parameters, is 0.6044. So the value has been set to 0.02. So what has happened is it keeps on increasing the number of elements and sees, does the iteration again. What you can see out here is one thing, at 2454, the value between previous elements and the new elements has come down to 0.17385. Give a clearer picture, you can assume, let's say if a Gauss-Seidel method is running or Gauss-Jordan is running, or let's talk about even bisection method is running. So in all these three cases, what we do, we compare the results of the new case with the previous case. These are the computational techniques. So what we do, let's say in Gauss technique out there, we put the values, plug in the values x, y, z, 0, 0, 0, find the value of z, then we find the value of y, find the value of x. Repeat it again. Just hold on a second, please. Just a minute. Okay, fine. So it keeps on doing this, and what happens? Let's say the number of elements are 23,000, 21,000. So it has already come down below 0.02 to the value of 0.10. In the next step, what has happened is it has increased the number of elements again to see if the values are further decreasing or not. And this can be verified out here. You can see the value should keep on decreasing at every iteration. That is what we are assuming. But it might not be the case. The value sometimes might rise. So what it has done is, after coming below the specified value, it has checked it again. And finally, the value is decreased. So that number of elements will be taken into for calculation. We will check the results now. Go to results, create terminal solution data report. You can see on the top. Or other option is you can right click on results, create terminal solution data report. rectangular plot. Next step is S parameter dv, click on new report. So once this report has been generated, select the red line that you can see out here, right click, marker, add minimum. So you can see the value is coming close to 10.054 and it's minus 16.9 dB. And we will check the bandwidth. So right click, marker, and add Y marker. Select the Y marker, scroll down and change the Y value to minus 10 dB. So the bandwidth is 10.18 minus 9.93. So it's close to 0.25 gigahertz or 250 megahertz. And if you have to calculate the percentage bandwidth, so that will be del f upon fc. So del f is 250 megahertz and fc is 10.054 gigahertz. So we have to make a calculation, and based on that, the percentage bandwidth or the fractional bandwidth can be calculated in this case. Next step is we can see the other parameters also out here. What we do is go back to HFSS design. Now, these are some of the techniques let's discuss. First of all, when you are simulating any antenna, if it is any structure out here, let's say, if it is a narrow band structure, let's say we are going to see the performance over a narrow range of frequency 2 to 3 or 3 to 5 gigahertz. In that case, what we do is we always go for we can go for all the three: in discrete, interpolating, fast. Fast takes the least amount of time and gives you the result. But the thing is, as we move higher and higher from the away from the center frequency, let's suppose if you have got a setup frequency out here that I have specified out here, the setup frequency was 10 gigahertz. Fine. And we are solving it between 9.1 to 10.9. So it's pretty close. So in this case, we could have gone either for discrete, interpolating, or fast. So fast would have given the results quite quickly, and the results would have been accurate, let's say good enough for our purpose. Good enough means accurate enough that can be utilized. But if your bandwidth is quite high, let's say instead of going from 9.1 to 10.9, had we started from let's say 5 gigahertz to 15 gigahertz, in that case the fast would have generated results, but those results would have been inaccurate. Hence, we do not go for that. We would have gone for either discrete or interpolating. Now, discrete works in all the three cases. In any case, discrete is work. But the problem is discrete takes a lot of time. So what we do is the trick here is usually if it's quite narrow band, you can go narrow band. Let's say you can go for fast. If it is wide band or something like that, let's go for interpolating as we have done in this case. So we have gone for interpolating, and when it comes to the frequency of interest, right now let's say our frequency of interest in this case is 10.05. So what we will do is whatever the frequency of interest is that there only on those frequency points we are going to run the sweep, or let's say the discrete sweep. Let's take an example. Let's suppose I'm interested in 9.93, 10.18, and I'll just note it down here. Um, so I'm sharing this here. Okay, so I'll note down the frequencies: 10.05, 4, it's gigahertz. Another one is 9.93 gigahertz. So I'll note that down. And the third one is 10.18. So the thing is, you are getting the best of all the things. Thing is, fast is fine, but right now what will happen is interpolating will give you the quick results. The most amount of time is taken by discrete, it gives the best results. Next comes interpolating, it calculates the result at certain points, and on the other points, what it does, it interpolates the value. In the third case, fast, it calculates the value on its own algorithm and gives you the result. So fast gives you the result in the quickest time, but with most inaccuracy. Interpolating takes somewhat more time, the results are somewhat accurate, and discrete, the results are most accurate compared to these two, but takes a lot of time. What we do is we are going for interpolating. So it trade-off between time and accuracy. It gives good accuracy, and time is also less compared to discrete. That has been done. Now the three frequency of interest that we see out here, we are going to put on a discrete sweep on this. So how to do that is right click on setup one, add frequency sweep, and let's say we are going for discrete and linear count. Suppose we are changing it. Let's make it, suppose initially I'm making it as 2, and instead of linear count, I'll make it a single point sweep. So single point sweep, the first frequency is, let's say, 9.3 gigahertz. Save, fine. Next point is 10.18. Sorry, it was 10.054. So 10.054. I'll add another one, add below. So third one is 10.18, 18 gigahertz. Save fields for all the three cases. Click on OK. Now what I will do is I'll right click and run analyze. So for these three cases only, the field values are saved. We need to run the discrete sweep. One more reason is to save the field values. If you are running interpolating, the field values are not saved. The field values are saved only in the case of fast or discrete. This can be viewed here. If I'm giving interpolating, you don't get this option out. If I make it discrete, the option is present. If I make it fast, the option again comes here. But for interpolating, the option is not there. This is one disadvantage. Hence, what we do is interpolating, we calculate everything out here, and then we run a discrete sweep. It is not a disadvantage, it is kind of an optimization to run the interpolating at our required frequencies, and then whatever frequencies we are interested in, those frequencies we extract and run the discrete sweep. So it is running. In the meanwhile, let's see other results. This is a patch out here. So the question about inset, right? So let's see. So for this moment, I'm removing this box. So I select this box and click on this icon. So this is gone. Now what has happened is, here in the left hand side, the voltage is maximum, and this hand the voltage is minimum. At center the voltage is 0. So here it's plus V, 0, and minus V. And the current is 0 at this end, and the current is 0 at this end, and the current is maximum at the center. So based on that, you have to calculate the impedances. So Z is equal to V upon I. So here the voltage is very high, so the impedance will also be high. Here also the voltage is high, hence the impedance will be quite high. And at the center, Z is equal to V by I. So V is equal to 0. Hence impedance is also going to be 0. So that means between the center and any one of the edges, we could have connected this feed line to this side also, like this. So between the center and one of the edges, the impedance somewhere is going to be 50 ohms. Now, according to maximum power transfer theorem, what we are doing out here is we are using a port of 50 ohms out here. Now 50 ohms port is connected to this 50 ohm microstrip line. This feed line that you see out here is made up of 50 ohm due to previous calculations, and it is meant for transferring power from this point to this point. Now we cannot directly connect it to the edge in this case. So what we do is we find a point at which the impedance is going to be 50 ohms. So at this edge, let's say at this length out here, the impedance is going to be 50 ohms. So what we do is we cut a part out here and connect this. So this is the inset that has been cut out here. So let's check the other results and then we'll verify for other things also. So go to radiation, right click, insert far field setup, infinite sphere, go for this. Theta, we make it 0 to 360. Click on OK. Then we have seen the results, the near field results, and for far field results, right click on results, create far field report. This option will only come when you have created the infinite sphere. Click on radiation pattern. Now we'll see the result in the XY XZ plane, in the YZ plane. So let's check the electric fields out there. Let's see. So infinite sphere one is there, gain is already there. Let's select gain in dB, families, phi. Let's take it for phi equal to 0 degrees. And then phi is equal to 90 degrees. At 10 gigahertz only, let's check it out. New report. So we can see the values. Okay. Now what we'll do is we'll make it a bit more fine. So I'm deleting this and plotting it once again. Right, results, far field reports, radiation pattern, dB, families. We go for first phi is equal to 0 degrees. and new report, and then again select it, go for 90 degrees and new report. So two reports have been created, and this we can visualize out here. So go to field overlay, right click, plot fields, radiation field, make click on both of them, apply and close. So this is, you can visualize the field which are drawn out here. The E-plane field and the H-plane field that have been drawn out here. You can visualize any field based on this. And second thing is, like, fields are always created with respect to origin. Always. So even if your antenna was placed anywhere in the space, so this field will always be created at the origin. Next step is, let's see 3D pattern for this case. Right click on results, create far field reports, 3D polar plot. So finite sphere 1, let's go for gain dB, fine, new report. So this is the pattern in dB that you see out here. And let me create one more pattern with none, absolute values, and new report. So this patch antenna is highly directional, not highly directional, it's a directional antenna. So this we can see it from here. If I click on field overlays, plot fields, radiation fields, this is gain plot 4. What I will do is I will remove the tick marks from here and go for only gain plot 4. And let me increase the scale to 0.5, apply, close, and this you can see it here, how the pattern looks like. And if you have to check the parameters in this case, complete antenna parameters. So for 10 gigahertz, we can check that the activity is high, the peak gain is also fine, the realized gain is fine, system gain is 6.16, radiated power is okay, and front to back ratio is 383. Means the power in the front direction is at least 383 times stronger than the power in the back direction. So for 10 gigahertz, and also you can see the fields. So the fields are maximum in the x direction. You can see it here. The x, the value of R into E. R is the value of volt per meter. Sorry, R is in meter and E is volt per meter. So this gives you volt per meter into 1.916 at 356 degrees and theta 176 degree phi. So 376 degree theta is this, 376 degree theta, and phi is equal to 176. This is, you are getting phi is equal to 90, 180, somewhere out here. So these are the two things that we have seen out here. Now let's talk about the different feeding techniques. This is one of the feeding techniques called as inset rate. The problem in such a case is, the inset that you see out here, it is meant for the feed line that you see out here, it is meant for transferring power from the port to this end. But the problem occurs, there is also some amount of radiation from this inset also. Sorry, not the inset, the microstrip feed also. So that results in a lot of power loss. So what we have got, we have got other techniques so that it becomes more efficient. And you can also make a analysis of different modes and current densities out here. Select the patch, right click, plot fields. You can go for E field or H field. Let's go for vector E field, 10 gigahertz. So this is the E field. As we talked about earlier, the voltage are maximum at one end and minimum at one end. So you can see electric field is equal to volt per meter. The voltage, suppose minima at this end and maximum at this end, center it's 0. Hence V by I. So voltage will be maximum at, the impedance will be maximum at this end, maximum at this end, and at the center it will be 0. Z is equal to V by center, it will be 0 because I is 0 out here. Second thing is, based on this, select this, assign plot fields. Let's try to go for uh, surface current density. So this is surface current density that you see out here. So we can go to field overlays, right click on JSON, modify attributes, change it to log, and change the plots from fringe to make it, let's say, 2, so it will become more clear. And then you can see at the edges the surface current density is high. You can animate it also, but animation takes some time. But you can try to animate and see at which places the current densities are high. So those are working in slots or other cases. Wherever the current density is high, if you make certain changes, make certain deformation in the structure as at those places, you might get certain closeness of the frequencies, or you might excite new modes. And second thing is, this antenna is not radiating only at 10 gigahertz, but it's going to radiate at higher order frequencies also. So the purpose of making the slots out there is to bring those impedances closer. And we can check the final impedance plot also. Right click, rectangular plot, go for terminal Z parameter, and go for imaginary and real. We report. So this you can see it out here is marker, add X marker at 10 gigahertz. You can see the real part is 63, fine, and the imaginary part is minus 70 and 10.054. You can see it out here, 0.00345. The real part is close to for 50, that is 47, and the imaginary part is minus 40. So if you're designing any case of antenna or something, the real part, if you are matching it 50 ohms, so the real part can go to 60 also, the real part come down to 40 also. That is not an issue as big as having an imaginary part. Imaginary part in this case is capacitive in nature because you are getting minus symbol out. So it's 47 minus J 14.02 ohms. So your purpose will be to at suppose particular frequency. So we are talking about 10.04. So at this particular frequency, we have to see the imaginary part minus 14 capacitive in nature. So we have to design a certain structure such that that has got an let's say inductance nature at 10.04 gigahertz that will negate out this. So in that way, you'll get a good matching, and just we'll see that now. So what we'll see is, if this is a structure right now out here, what we'll do is we will make a simple optimization of this length out here. So how to do that is, let's suppose this length that you see out here, this is defined by Li, length of inset, this depth out here. Now the length of inset was given as 0.295. Let's suppose I make it 0.395. So you can see this has increased. I'm removing the current plots for the moment. It is 0.395. So what I will do is I'll make it, I'm making it back to 0.295. You just pay attention here. So what is happening? The moment I click on enter, this is reduced. So what I will do is, or if I make it 0.195 length of inset, it is further reduced. So I'll make it back to the nominal value 0.295. Now what I will do is I need to make sure that if I'm increasing this inset distance out here, if I'm increasing the inset distance out here, how is the matching improving or not improving? Either way the case. So I'll select Optimetrics, right click, add parametric, select the variable from here, add length of inset. Let's say 0.295 is there. So I'll choose 0.295 is already there. I'll choose 0.300. And let's say next point, let me choose that. Let me go for single points for the moment. Single value. Let's say 0.3. I'll add another one. Let's say 0.315. Add 320. Add and 3 to 5. Let's say 3 points I've added. I could have also gone for a linear step also. Anyway, you have to add the value, whatever it is you can find. Click on OK. Four values. Click on OK. Fine. Now I'll select this parametric setup. Right now, I'm not interested in calculating the other values. So what I will do is, or the discrete point values, I'll go to General, Setup 1, that is fine. Click on OK. Then right click Parametric Setup 1 and Analyze. So since we have run total 4 variations out here, and if you are using HPC, the high performance computing, you can see the 4 variations running at the same time. Once the simulation starts, we will move to the other feeding techniques. The meanwhile this is done, I'll close this window. Fine, it has started. Show progress. We can see in my system 4 variations are running at the same time. 1, 2, 3, and 4. You can all do it in the systems that are there. You can increase the number of cores. So in ANSYS HFSS, you can utilize at most without HPC license, at least 4 cores can be utilized at the same time. Beyond that, the HPC license is required. But the good thing is, up to 4 things they are running in parallel. 1, 2, 3, 4 are running in parallel. So this you can do it. I'll show you a quick view. Go to tools, options, HPC and analysis options. You will have local machine out here. Click on edit, and here you can put the number of cores to 4 and number of variations. Let's say I can make it 2. Number of cores is number of systems. Number of variations means number of tasks. So 4 tasks on 4, that is fine. 1, 1, 1, 1, or 2 on 4, whatever is there. But you cannot directly increase the number of cores. You have to check first of all in your system how many cores are there. So some of you might be using high-end system, but at least only 4 cores can be utilized in normal HFSS license. So it is completed also, and let's check the result. Results, right click, create terminal solution data report, rectangular plot. Go to families, you will see insert all the values will be shown. Okay, it's still running. Fine, still running. Okay, it's still running. Once it is done, it will show it there. In the meanwhile, let's go to the theory of some other things. So this is, you have seen how the parametric design is done and why the insert is made. Now, in the other cases, the design is made. So this is the design that you saw right now, the insert fed antenna. Same design. The copper is on the top, the ground. This is made for a different case. Second one that is important is the edge fade. This you can see it out here. Now, the theory goes like this. This is the antenna out here, patch antenna. Or let me make it like this also. So this is antenna. Earlier we talked about not connecting at the edge. The reason for that was the edge of the impedance at the edge could have been anything. Now what happens? Suppose we are able to find the impedance at the edge. Let's suppose just for say it's Z edge, or let's say EDG, Z edge. This is the impedance at this place, and the center the impedance is 0. I don't want to make any inset or anything. So what I will do is the impedance, this is known from the calculations. This is suppose a Z edge, and here the port that we are using is a 50 ohms at this edge. 50 ohms. So this is also 50 ohms. Now this is 50 ohms, and this is Z edge. Let's say 300 ohms, or if any ohms, 300 ohms out here. So to connect this one to this one, what we are going to use is a quarter wave transformer. The quarter wave transformer we use to match two different impedances. So the value of quarter wave transformer will be calculated as follows. Since this is suppose 50 ohms, let's suppose the edge impedance is 100 ohms. Just for now, 100 ohms. So the value of the impedance of this quarter wave will be under root of 50 into 100. So that comes out under 5,000. So it will give you certain values, 70 or something, not sure, but it will give you certain values. So under root of 50 into whatever the impedance is there, and the length will be equal to lambda by 4. So this antenna is suppose resonating, let's say it's designed for 10 gigahertz or 20 gigahertz. So this length will be equal to lambda by 4. So this is how we are going to use the edge fade in this case of patch antenna. This one. And the third one is profit. Multiple other things that also we discuss. I'll show this example also how this profit has been done. So in this profit again the same thing has been done. you have to find out the place where the impedance is 50 ohms, so that you have to make calculations, analytical calculations. And once that has been done, how to connect the antenna out here. So this is important. So let me show it out here. Let me take a new design. This is coax. This is important how to draw a coax. So suppose you have got a ground out here. Fine. Let's suppose everything is at a center. Let's suppose at the center you are getting any impedance we have to connect. It will be easier. So let's suppose I'm drawing a substrate out here. The substrate is of, let's say, Rogers or TIFF. Let's say fine, ultra laminate. And on the top there is a patch. So this is the ground. This is the substrate. Fine. And this is the patch. Fine. And the ground also will increase somewhat. This is there. Now what I'll do is I'll make it certain to patch go to the top. So height of the substrate is 0.2 millimeter. So the patch also will be created on the top. Let's 0.2. Okay. Fine. This is done. Now next step is, first thing is how to draw a coax. First of all, draw a cut where the coax has to be connected. So the cut will be drawn here. Suppose from the center, so I draw a cut here. So the radius is 0.1 mm. That is fine. So this cut has been drawn. Fine. Now the ground and the cut has to be subtracted. So I subtract it. Select the ground first and the cut next. Go to modeler, boolean, subtract, and click on OK. So you can see the cut has been made. Next step is draw a cylinder at the same place. So I'm drawing a cylinder, suppose here. Fine. The cylinder has been drawn. So I'll name it as outer conductor. So the material, let's keep it Teflon. I'll explain the reason why. Click on OK. And the cylinder that has been drawn, let the radius be 0.1, the same as the cut. Okay. And let me increase the thickness, transparency. So this is the outer cylinder that has been made. Fine. Now what we'll do is we'll make it another cylinder. So this will act as the outer cylinder. Now we will make another cylinder. So let's say make another cylinder. Select this. Same height. So I'll make it as inner conductor. And this one, let's make it of copper. Or let's say PEC, perfect electric conductor. Click on OK. Achha. Probably this is okay. The system has hanged. Just a minute, because the results are updating now there. You can see by mistake it has gone to non-model. You have to make it correct because I made a tick mark out there. You have to make it model. That makes you okay. So right now we have got two cylinders. This is the outer cylinder, the outer conductor, and this is the inner conductor. Okay, the results are updating, hence there is a delay out here. Okay. Why is it so pass number 16? Fine. Once the pass is complete, it will start. Okay. So it will create some issues, but not very much. So this is the outer conductor. This is the inner conductor. So let me make it in a different color. So it will clear it. Let's say the outer conductor is, let's see, okay. This is fine. So it's not getting much updated because the process is running in the background. Once that is complete, it will be updated. But for the moment, let's find if the color is also not coming, but we are able to see the outer conductor fine. And for the inner conductor, what we will do is we'll change the value of the radius. So radius is 0.1. Let's make it 0.05. Fine. Now you're able to see the outer as well as the inner conductor. The two are done. And third thing is the inner conductor itself, we will make it extended into the patch. So what we'll do is inner conductor, let's select this, copy and paste, change the name to feed pin, click on OK, and let's start height will be, it's 0.2. So you can see right now, this is the outer, inner, and the feed pin. Fine. This is the outer conductor, inner conductor, and the work is not completely done. Now what we will do is, fine. Now what we will do is right click, create on selection mode, go to faces. What I will do is I'll the face of this outer conductor. You can see I select only the face because inside it's totally clear. Select the face, right click, assign boundary, go for perfect E, click on OK. Now your conductor is complete, the coax is complete. Why? Because this entire material is made up of Teflon, and outside that you see now, this is conductor, that is perfect E. Inside it is Teflon, and again inside you have got copper. So one conductor, two conductor, and inside it is a dielectric. So this is the thing that has been drawn. Now to provide its excitation, draw a circle exactly at this place, starting from center and touching to outside. So this is drawn. And finally, what you do is draw a port cap. A port cap is required so that since if you are going to assign this as a wave port out here, so in such a case, the port cap will prevent the waves from coming outside. Like if you are suppose, let's take an example. If you are designing a wave port, in the wave port, what we do is draw a simple structure, let's say rectangle or a circle, and assign is wave port. But we have to assign in that case in which direction the wave is going to flow. So how we do that is the opposite side we block it with the help of a conductor. So here also we will do the same thing. Circle 2, select it, copy and paste. And this is circle 3 right now. You can see it out here. We'll right click on it, edit, thicken sheet, surface, thicken sheet. Let's say I'm thickening it to initially just for us checking it. Let's say I'm going for 5 mm. So it's going in the forward direction. What I will do is I'll go for minus 5 mm. Just for verification. Now it's coming in the down direction. Now we do not require such a big conductor. So what we will do is thicken sheet, and instead of minus 5, the value is 0.01 mm. Okay, you can see that this is made, but this is yet made of vacuum. So what we will do is select this, assign material, and make it a perfect conductor. Easy. Okay. Now what has happened is you have got the port out here. Now where is the port? Patch is there, ground is there. This is the port. I'll rename it port. Okay. On one side of the port, you have got this conductor, which is blocking one side, and hence the waves starting from the port The wave starting from the port out here will go only in the forward direction, okay? And then through the hole that you see out here, the hole that you see, that we have created, it will go and excite this patch. So I hope the results are complete, still running. So this is one of the techniques, the coax. So this coax, you can draw it on any structure. And if you're going for a filter design also, you can use this coax. So this is one of the designs. So this was the edge that we saw. The inside is already shown, the results are running, optometry results shown, and this is the probe feed. The probe that we are choosing out here, this is a 50 ohms. So according to the formula to calculate what is the radius of the inner conductor and the outer conductor, that will give you the impedance of 50 ohms. So this is running. Okay, it will take some time, but even if it takes time, I'll show it. I should have made it fast. But anyway, interpolating will give you better, accurate results. And apart from this, these are some of the feeding techniques that you saw. There are two more techniques. One is the aperture coupled, and one is the proximity feeding. In aperture coupled, what is the plan? Let me show it here itself. So this is the probe feed. I hope this is clear. I'll just give a brief idea of what is aperture coupled feeding. So this is the probe. So let me delete everything related to probe. Inner conductor also to remove it. Subtract I did. So subtract I'll remove it. Circle remove. And port also remove. Fine. So let's talk about aperture coupled. In aperture coupled, what we'll do is the ground will not be made here. This is a substrate. What we'll do is we'll select the ground, and let's say the ground, the total height of the substrate is 0.2 mm. So let me make the ground higher. So I'll double click on it, and the ground is 0.2. So I'll make it as, let's say, 0.1. Now you can see where is the ground. The ground has come in between. Now the feed line will be drawn on the lower end side. So I'll draw the feed line here. Let's suppose I'm drawing the feed line. So now is it clear? So the feed line is the bottom, the patch is on the top, and in the center there is the ground. So let me color all these things differently. The patch, since it is a conductor, let me put it orange. Okay. The ground is also a conductor. Okay. And the feed line is also a conductor. Fine. You can see the three structures out. Okay. Right now, there is no connection between this. You can see the feed line and the patch because there is a ground in between. So what we do is we cut a slot in it. What we'll do is we'll cut a slot in the ground itself. Let's suppose we are cutting a slot at this position. So the rectangle that is made, I will name it as slot. Okay, and it will be cut at the same level at the ground since we are cutting it in the ground itself. So you can see the slot has been cut. It's not cut, it says made in the ground. Now I'll select the ground and the slot and subtract them. Draw for the modeler, Boolean, subtract. So ground minus slot, click on OK. So you can see the ground has now got a slot. Now the electric field lines will start from the ground and they will pass through the slot and meet the excite the patch on the top. The patch will be excited at this place. So in this case, two things are happening. First thing is the whatever radiation is coming, let's say, is being generated from this feed line. So that will remain a substrate itself. It's not going to come out. And second thing is most of the radiation will be coupled through the slot itself into the patch. So this is what we call as aperture coupling. And there is one more that is called as proximity coupling. In proximity coupled, what we do is we just reverse this. What we reverse, so this is aperture coupled. So on the top is the patch, in the ground we have the slot, and below the ground we have the feed line. Patch, ground, and the feed line at the bottom. And the second structure that we can see, this is uh, aperture coupled, and there is something called as proximity coupled also. In that case, what we do is, let me remove this slot for the moment. The ground, we keep it here itself. Fine. I'll move the ground, sorry, the ground I will move below. Let's move below. Okay. And this is one substrate. We will draw another substrate. Then I'm drawing another substrate. Copy and paste. So this is superstrate. Let's say this is a lower material. Let's say it's a lower value permittivity. Let me make it so the tradition is better. Let's say FR4. Okay. And okay. And let me create it from 0.2 itself. So this is there. And the patch also, let me send it to the top to that is 0.4. Okay. And the feed, this will be at 0. So this is what you call as aperture coupled. Sorry, proximity coupled. In this, you have got substrate 1, superstrate out here, ground on the lower end side, ground, feed, and the patch. So you can see the structure. Ground is here, the patch is here, and the feed is here. Three things: ground and patch and feed. So the ground and the patch feed are there, so they will be coupled together. Means they will connect it together, and whatever the lines will be coming out from the feed line, they will be passing through the superstrate and coming into the patch and feeding it. So the length is not correct. You have to reduce it so that it's fitting its direction. Let me reduce it. It should be reduced in the x direction. So x size 2. Let me make it as 1. Fine. Now this is how you feed in the case of proximity feeding. So aperture you saw, proximity you saw, probe feed you saw, edge coupled, and normal insert. And you have also got CPW. In the case of CPW, you have got coplanar waveguides. That means the feed will remain here. And the ground plane, which was earlier on a different plane, means this is z equal to 0. This is z equal to 0.1 and 0.2 and 0.4. So in that case, the ground and this all will be on the same plane. Let's take an example. Let me come to a different plane altogether. So let's say I'm showing it of the substrate. This is one. So here will be, let's say, one plane, one ground. Here will be another. And this is the feed line. And whatever structure you have got out here, whatever structure. Let's we can connect it here. Bottom we can keep the substrate. Here is the same. If you are going for any kind of ultra wideband or super wideband design, cases you 90% times you have to go for this. And second thing is, in this structure, if you're going for coplanar waveguide structure, the variation, like in these two cases, in this case the permittivity of the substrate varies with frequency quite highly, but in this case the variation of permittivity is assumed is said to be constant over a range of frequencies. So if you're going from, let's say, 4.4, so it will remain constant over a range of frequencies. It's from 2 to 10 gigahertz or 15 gigahertz. So for wideband or super wideband, ultra wideband, you generally have to go for coplanar waveguide structure. Feeding in this case has to be done using wave pool. So you have to draw a rectangle. Let's say it's XY. I have to make it in YZ plane. So I'll change it to YZ. Draw a rectangle here, which is like this. And it's drawn there, but it should basically be drawn up here so that it touches both the sides. So the simulation has been complete in the previous case. So let's check it out. So the parametric design has been done. What I'll do is go to results, right click, terminal solution, rectangle plot, families, all. So you can see the four variations will be there. 1, 2, 3, 4. The first is a nominal 0.295, which was the initial value, and rest are 1, 2, 3, 4. So click on new report. So you can see the first one 0.295. So we are getting at minus 15 point something, minus 16 point something. But as we are moving the feed line inside 0.3, you can see first of all the frequency is shifting and the matching is improving. Next case, you can see the matching is improved to how much? Minus close to minus 33 or 34, and in this case you can see it has come to close to minus 40. So I'll select it, right click, marker, add minimum, so it's come to minus 37, and we can verify this from here. One thing we are drawing conclusion is, as we are increasing the inset length, the gap out there, the distance from the edge out there, in that case the matching is improving. That means the imaginary part is decreasing further and further. So we'll verify this from terminal z parameter. So let's plot only the imaginary part for the moment. New report. Let's check at minus 10 itself. Marker, add, X marker. So this you can verify. At first it's minus 17, minus 13, minus 3, 0.29, 4.32. So it has become positive in one case. 0.29, 0.4.32. So the thing is, it has come from minus 17 to 0.2, 0.02, 0.29, 4.32. So it has become finally inductive in nature. So the imaginary part is getting lower and lower, hence the reflections are decreasing, the power loss is decreasing. So with this, if you have any doubts, I will let the questions open to you, or as sir says.
Thank you, Engineer Akash. Sir, thank you
Thank you, sir.
for your demonstrations, presentations. So now I think we can take some of the questions for participants. So may I read the questions now?
Sure, sir.
So let me start from one side. There is a question: do our measured result will vary if we will not connect SMA conductor during simulation?
Look, measure results will of course vary. They will vary. The reason is the measured results will vary because your matching is going to change. The SMA connectors are meant to transfer power. Fine. So what happens is, here what we have done is we have taken a ideal connector whose impedance is 50 ohms. So why that is done is, initially when we are checking a design, we are more interested in towards designing the structure. So once the structure has been designed, then what we do is we check the coax or whatever is there, and suppose you are getting a return or any parameter at minus 50, minus 60. So when you check it, so in real life you are going to use an SMA connector. So the moment you put an SMA connector, so that was if not taken into simulation, so the results will of course vary. So for that, what you have to do is take a 3D component of the SMA connector. It's available on the sites or internet out there. Their CAD model, place it here and check it. Now, if you are using the same SMA connector which you are buying in the market and connect it to the antenna, and the same SMA connectors 3D model or CAD model you are using for simulations, the results will be same. Let's say up to 99% similar.
Yes. Okay. Thank you, sir. The next is, sir, how to calculate the impedance of feed line or any quarter wave line? Can you share any document with formulas?
For that, on internet, if you select microstrip line calculator, you will come to across many sites. Okay, so I suggest you can go through that one once. On internet, just Google microstrip line calculator.
Okay. Thank you, sir. So there is next question related to equivalent circuit of antenna.
Right, equivalent circuit. So fine, I'll share the screen with you and I'll show the pros and cons of it once more. So let me share the screen. So equivalent circuit. Now first thing is no software is there out there, okay, which can give you the meaningful. I'm talking about meaningful equivalent circuit which is generated. So suppose I have to generate the equivalent circuit. HFSS of course does that. Let's suppose I'm going to results, solution data, fine. You can go to matrix export. In matrix data, you can see here export and export equivalent circuit. So this is the format. PSpice, Spectre, HSpice, Twin Builder. I can choose anything. Let's say I'm going for PSpice only. Documents and soft. It will be done. Okay, fine. The equivalent circuit is exporting. Now two things into it. First thing, the equivalent circuit that will be exported from here will be RC tank circuit. RC. In any, so what happens out here is when you are exporting the equivalent circuit. So if this is the graph that you are getting, normal graph. What HFSS will do is for any software, they will take one RC, connect in series, RNC in parallel, and the combination of RC in parallel will be in series with other RC, RC1, RC2, RC3, RC4. And changing the value of R and C, resistors and capacitance out there, this graph will be fitted. So the graph fitting is done, and you can say that RC component is fine. But why I'm talking about it is not meaningful is because if you have actually generate the equivalent circuit, so the step of doing that is divide this structure into smaller components. So this structure can be divided into, let's say, two parts. The first is the microstrip line feed, and second is the patch. First step. Second step is do an analytical study. Take an analytical study how to model a microstrip line. So in that case, you will be able to generate a equivalent circuit of a microstrip line. Second case, do an analytical study of the patch antenna, rectangular microstrip patch antenna with the ground on the other side, and generate an equivalent circuit of that. Then add them together, means you can put them together. Directly, any software, whatever gives you the equivalent circuit, that will not be accepted unless you put a reason why that equivalent circuit is there. So let's suppose, just take an example. Here we are getting, let's say, one gap is here, another gap is there. So we can say there is small amount of capacitance in this case, this side, this side. So okay, we model this gap with the help of a capacitance out there. This line has capacitance, inductance, and this as a resonator, the patch as RLC out there. Then you have to connect them in series on or parallel depending upon the configuration, and finally get there. So the equivalent circuit which any software gives you that match you with the S parameter. But when someone asks like, what is the meaning, why you have used R there, what does this C represent? So at that time, the software cannot define what is the meaning of an R and C, for what component do they stand for.
Okay, sir. Thank you. And the next question is for MIMO antenna, what type of boundary will radiation box have?
For MIMO antenna also radiation, okay, fine. In case of MIMO, two things can be done. First thing is, okay, we will be discussing this on the third day, but it's the final day. But for MIMO antenna, we are going for these elements which are in phase, which are phased. Let's say out of phase or a phase difference is there. So initially what we do, we select a single element and make a unit cell of it. And then using master slave boundary condition, we make a periodic arrangement of that. And on the sides will be master slave boundary. On the top, we can put radiation or PML. But if you are going for, let's say, explicit means if on a single substrate, let's say in this case, okay, let me share the screen once again. Let's suppose this is the antenna. Just a rough example. So this is the antenna. I selected all, duplicated, move. So let's suppose, okay, fine. This is, I'm keeping it. Okay. Okay, it is on different, but suppose it's on a same plane. Suppose these substrates are united and everything. So let's take it. This is in suppose 0 degree. This is at 45 degrees phase. So if this kind of structure you are drawing, which everything is united and everything, in that case you have to take a bigger radiation boundary and radiation boundary in all sides. But if you are going for a domain decomposition method that we will be discussing on the final day, in that case you will have periodic master slave boundary here, and that can be repeated n times. It will become clear on the 5th day.
So I request the participants to for this MIMO question, please wait for the last day. So after that, if you had any query, then you can post it again. So I'm reading next question.
Right, sir.
How can we use CPW feed with already designed fractal antenna using HFSS? And there is a related question also. Please tell me the procedure for CPW feed excitation.
Okay, so for CPW feed excitation, a rectangle has to be drawn, okay, or a structure has to be drawn that will cover, as I showed here, CPW itself. For CPW in this case, let's say where is this rectangle made from? So this rectangle is named as rectangle 4, 3, 2, 5. So we have to check about the minus x. Just a minute, rectangle 2 minus 1.2. I will move only the x direction, so this will keep it as 0. Okay, and the 0 will show it here. So if I make it as let's say 1. Fine, let's suppose it's touching exactly here. So this rectangle that you see out here, this should be placed like this exactly here, and it should cover it completely. Something like this. It should cover it completely. So the feed line should be properly covered, and both the sides, the left hand side and the right conductor, some parts of it should be covered. The left and the right hand side, some parts of the conductor should be covered. And once this is done, select the rectangle this that you have drawn, right click, copy and paste it. Rectangle 6, Control C, Control V. This is done, paste it. Select rectangle 7, go to edit and thicken sheet. Make sure it's always coming out. Once I click on surface thicken sheet, so let's say I'm making it as 5 mm, okay. So it's going inside. What I will do is thicken sheet, make it as minus, let's say 0.01. So I'm sure now it is going to come outside, okay. So it has come out, and select this and make it as PEC. And name it as port cap. So this will prevent the waves. So you have got a rectangle out here, correct? This rectangle. Rectangle 6 is out there, and just behind rectangle 6, just behind it, you have got this port cap. Just behind the rectangle, you have got this port cap that can be seen here, right? This is a port cap. And there are certain standards for defining it, like what is the width and the height of it. I'll share across the video. That's mentioned clearly, like what is should be the width of it and how much high it should go. But this is a basic procedure. At this edge, we are going to connect it. So it's right now on this side, but it's considered it to be here. Right.
Yeah. So thank you, sir, for demonstrating this CPW. And the next question is how to find S parameter of a conducting strip which is used to connect between the transmission line.
S parameter of a conducting strip.
Which is used to connect between the transmission line.
Okay. So, okay, let me try to address this way. The S parameter we give, like we have got one port and second port. So the S parameter gives the property of the device which is connected between the two ports, port 1 and port 2. So if even in transmission line or any other case, if we are able to model the transmission line first of all in HFSS, okay? Suppose you have got the model ready, and the next thing is whatever you're using, you just place a port at one end, place the port at other end, and try to check it out.
Yeah. Should I read next question?
Sure, sir.
Okay. So I will be taking 2 or 3 more questions before closing. Yeah.
Right, sir.
So how to see modes in HFSS?
How to see modes in HFSS? So in that case, what has to be done? Suppose this rectangle itself I have defined, this rectangle. So I'll select this port that you can see out here, right click, let's say assign excitation. Will throw an error probably. So it did not throw an error. Integration line. So number of modes that I have to see. Again, what kind of modes is being specified here?
So no mode has been specified. Just question is how to see modes in HFSS. I think it might be referring to TE, TM modes.
Okay, in that case, again, if it is a waveguide or any closed structure, if it is a waveguide or closed structure, you have to specify the how many modes you have to see. Suppose 4. Suppose I define integration line for this. Suppose new line. Suppose I define it at the edge itself, here to here, and let me copy it. Duplicate, copy from mode 1, copy from mode 1, and again copy from mode 1. Next and finish. Now, when I run this simulation, what will happen is I come down to excitations, right click, edit sources. Now by default only the first mode is excited. Now if I have to see what is coming because of second mode, I have to go here, make it 0 the first mode, and excite the second mode. Click on this and select 1. And this again, same way we can excite any number of modes that is required. So that is in the case of waveguide. In the case of antennas, if we are talking about the different modes which are present out there, so in such a case, what has to be done is you have to plot. Let's say this is the antenna. So I'm getting to Control Z. So this is the antenna. The results I think have come back fine. Select it, right click, plot fields. Let's say J, vector J. Surface fine. Plot it. That's the last done. So you can see the field distribution out here. Let me make it polar, modify attributes, scale, and marker. So this is, you can see the field variations out here. This is the first mode. TM probably 110 probably. This is the first mode. So this is based on the patterns of these vectors out here. You can calculate what is the first mode. Same way you can go for a second mode, third mode, fourth mode. So you have to plot at different frequencies. The modes you have to plot at different frequencies and based on the resonances out here. So the different resonances that you are getting out there. So at those different resonances, plot the vector J surface, or if you're able to correlate, you can also go for vector electric field also. And based on that, count the number of cycles out there. So those will give you the proper modes at that frequency.
Okay, sir. Okay, sir. Thank you. And the next question is how to draw co-pole and cross-pole.
How to draw co-pole and cross-pole. So that's simple. So if you're drawing co-pole and cross-pole, so suppose if I'm drawing this one, suppose this is, let's say we are calling it as co-pole. Okay. So anything that is orthogonal to it in the orthogonal plot. plot. So this is suppose phi equal to 0 degree. So orthogonal to it, phi equal to 90 degree. This will give you the cross pole.
Okay, thank you, sir. Then there are some of the queries regarding recording of the video session of this session. So I will be sharing videos of this session and as well as all the sessions with the participants. But those videos shall be shared during next week after all the videos has been finalized, and after that we will be sharing through Google Drive link. So I will be sharing all the videos, but during next week. So then. Sir, participants are asking for your email address.
So the thing is, you can put it at ansys.support@arkinfo.in. So whatever it's coming,
can you type from your side?
I'll type it, sir. I'll type it. Okay, is it visible?
Yes, visible. So interested participants can note down.
Okay, you can note down both of them.
Yeah.
So
okay, sir. The last question which I want to take up is
right.
How to do variations to a design while looking at current distribution on patch to get any desired aspects by using slots, DGS, etc.
That question is fine. So how to get this right? Desired, right?
Variations to a design by looking at current distribution on patch to get any desired aspects by maybe introducing slot or DGS.
Okay. So one thing is the important thing is, even if you're introducing slot or DGS, one thing is the place where the current density is high. Let's take example of in this case only. So wherever the current density is high, at those places, if you are making any kind of perturbation, so those perturbations are going to give you results more affected or more changed. But if those results are going to be in our favor or not, that is another thing. So that I cannot predict right now, and it cannot be predicted right now. But the thing is, wherever the current density is high, you can make changes. You can make slots out there to make your results affect.
Yes. Okay, thank you, sir. So if you, sir, permit me, I want to take one more question, which has been posted just now. Yeah. So how can we compose new materials which can be used for antenna design HFSS?
Okay, fine. I'll show it here. You go to, suppose this is substrate.